Does the flap of a butterfly's wings set off a tornado in Texas? This may seem like an absurd question to ask, but it was actually the title of Edward Lorenz's 1961 conference introducing fractal geometry and chaos theory to the world. What's fractal geometry? I'll get to that in a second. The name of this conference actually inspired one of the better-known names of chaos theory, with which you might already be familiar, the butterfly effect. In 1961, the meteorologist Edward Lorenz ran a weather simulation twice using slightly different initial conditions, but the results were strikingly different. This discovery demonstrated the butterfly effect, which is how tiny changes in initial conditions can lead to vastly different outcomes and chaotic outcomes in complex systems. If we knew every single detail about the starting conditions of an experiment, we could know what happens next, which means we could predict the future. I know, but because our tools aren't perfect, we can never measure everything right down to the last minute detail. So we have to use the next best thing: ensemble forecasts. Ensemble forecasts are basically when we're running multiple simulations with tiny differences in initial conditions to understand the range of possible outcomes. It's especially important in weather prediction, and it's what allows us to have a forecast up to about 14 days, but it can never measure everything with complete accuracy. But chaos theory isn't just about the weather. In fact, it's seen everywhere, from the double pendulum's unpredictable swing to the long-term behavior of our solar system. Even gravity itself is chaotic when examined closely. So things are much more chaotic than they seem. Now let's get to the good part, the math behind chaos theory. This is the Lorenz Attractor. It's a mathematical model created by Lorenz, you guessed it, as a simplified model for atmospheric convection. It produces a complex twisting pattern that never repeats, illustrating chaos theory's idea that deterministic systems, as in each starting point only has one possible outcome, can still behave unpredictably. For a large range of initial conditions, all of them will get on the Lorenz Attractor, meaning that each path is an infinite curve in a finite space. Since this isn't possible in Euclidean geometry, we have to look at another type of geometry, fractal geometry. It explores shapes that look similar at any scale, like the branches of a tree or the edges of coastlines, and can describe these complex patterns with simple rules. This differs from Euclidean geometry, which deals with flat, predictable shapes like triangles and circles, and it assumes space is regular and uniform. In contrast, fractal and chaotic systems show irregularity and an infinite complexity that Euclidean geometry just can't capture.